Yeah, is everybody back from break? Shall we go on? Yeah, you saw some first discussion about what's new in case of open strings as opposed to closed strings. Open strings have more risks of introducing boundary terms as you vary the Polyakov action. And the cure against nasty boundary terms is to impose good boundary conditions. And the two most basic choices that I discussed in detail are the following: that you either fix both endpoints of the open string in some spatial direction. This is known as Dirichlet conditions, and you have to make some choices of C and D, namely those places in the ith direction where you want to see the endpoint fixed. And other consistent choice is Neumann boundary conditions, where you impose the sigma derivative at the endpoints to vanish, and this is still compatible with having space-time momenta into these directions. And in both cases, Dirichlet and Neumann, we saw that the alpha oscillators were interlocked, so that there is no second oscillator species, alpha twiddle. You can just eliminate the alpha twiddles, and therefore have less building blocks to play with when it comes to constructing physical states. And for all of this, I used the language of maybe the first and the second lecture. Maybe you were already disappointed that I stopped using all the more advanced complex analysis framework, and now is the moment to go back to it. Now is the moment to explain how open strings find their place inside conformal field theory. And since open strings have this additional boundary, you have to enrich the conformal field theory by this boundary structure. The boundary CFT is about extension of conventional boundary-free CFT, such as to accommodate that extra structure of having a boundary. Yeah, my goal for now is to give a brief impression of that, what boundary CFT is. And for that purpose, let's go once more through all the mappings that we already did for the closed string. So we keep on complexifying the time on the worldsheet, or Wick rotating it. We keep on mapping that complex combination Z to the complex plane. And let's see what happens to the boundaries of the open string worldsheet. So the usual exponential map that took us from the cylinder to the plane, well, it will still take us from a strip to the plane. And let's track the fate of the two endpoints. So one endpoint for the open string at sigma equals 0, and the other endpoint at sigma equal pi. And as we plug this into the exponential map, then these two boundary segments are both landing on the real line. So the bulk of that worldsheet is then situated in the upper half plane. So this is the natural arena to do the CFT description of open strings. The upper half plane will describe the interior of the bulk of the open string worldsheet. Yeah, here upper half plane is filled, lower half plane is not filled, and the boundary is on the real line. So one of the two boundaries is filling the negative real half axis, and the other boundary filling the positive real half axis. And it looks as if they touch, but in fact it's the origin which still takes the role of infinite past. This is where the boundaries look like meeting one another. Yeah, and the agenda is to use as much of the CFT machinery as possible when we have this boundary as an extra structure. So let's see how we can accommodate that into a CFT-like framework. And sadly, we can no longer use the two independent copies of Virasoro algebra. Or, well, conformal transformations prior to the introduction of a boundary were all the meromorphic maps for Z, and independently all the anti-meromorphic maps for Z bar. So these were two, by themselves, infinite dimensional groups. And one of them is essentially lost. Instead of two Virasoros, we only have one Virasoro in presence of boundary. So in more formal terms, the conformal symmetry gets broken to a subset which preserves the boundary. So a very neat description can be given for the chart over here and for the zetas, where the boundary is simply the real line. So we are interested in those conformal transformations that preserve the boundary, aka which send real zetas to real zetas. So this is a quite useful characterization of the leftover conformal transformations. And now we want to have an analog of the earlier statement that the energy momentum tensor T and T bar were generating conformal transformations. How is it here? Which combination of T's and T bars is kind enough to generate the leftover conformal symmetry transformations? So first of all, the worldsheet became smaller. It's only the upper half plane, not the lower half plane. So the best we can hope for is that it's some restriction of T and T bar, which does this generator job. I should introduce the symbol for the upper half plane. I will write H, or this fancy H for the upper half plane. Yep. And this is where both T and T bar need to be restricted to. And this is not all. You furthermore need to make sure that at the boundary things are compatible. I mean, if both of them are living on a half plane, then the boundary is where the two of them meet. And we want to eventually integrate them, so let's make sure they are continuous. So there is a gluing condition, which requires that the two energy momentum components match at the boundary. Oops. So in that overlap region of where T and T bar are defined, they should better match. Yeah, and then we saw that contour integrals are an extremely useful computational technique. So we eventually want to have an open string analog of these Virasoro generators. So we want to eventually write down a contour integral like that. However, these circles around the origin become problematic. No matter how small I choose the radius, such circles typically go into a forbidden domain. I mean, both T and T bar are only defined in a half plane, so neither of them can be consistently integrated over that circle. So we need a kind of patchwork construction such that these circle integrals become viable. There will be one copy of Virasoro algebra that is constructed from a mix of T and T bar. So one copy of Virasoro modes instead of the two that we had in the closed string case. And for both of L and L bar, there was a contour integral representation, and I will preserve its structure, but I must be very careful what I mean by the energy momentum tensor therein. So if you drop these funny superscripts for open, then it's on the nose, the formula you saw in the closed string case. But now, what is this funny T open? So this is the way out from the dilemma that I just complained about. I want to integrate over a circle, but the circle is in both half planes. So I can't just put an individual T or T bar here. But what I can do is I can patch together the information from upper half plane and lower half plane. I mean, in the end of the day, it's an extremely simple idea. T has a half plane's worth of information, and T bar has another half plane's worth of information. Putting that together, you have information on a full plane. So you just stick these partial informations together and define this patched field, T open, in a way that for positive imaginary part, you grab the T on the upper half plane, and well, clearly the Z bar reflects upper into lower half plane. So when imZ is smaller than 0, then Z bar is in the upper half plane, and then you can consult T bar to have a sensible continuation into the lower half plane. So this is the right quantity to perform contour integrals of that type. And this is then the generator of the leftover conformal symmetry that is respecting the boundary. And if you got nervous about where it's an equality, no problem at all. That fellow is continuous because of the gluing condition. Yeah. So this is the kind of patchwork construction to have one species of T rather than two of that. And well, it is the same spirit of what we saw for the oscillators. Instead of attributing a separate life to del Z of x and del Z bar of x, you just form a merged version thereof. So the same kind of patchwork construction goes through for del x. But there is now a freely choosable minus sign. Namely, remember that T is quadratic in del x. So never mind the prefactor or normal ordering colon, but in view of this quadratic relation between T and the respective x derivatives, we have two ways of solving the gluing condition. There are two solutions to enforcing the gluing condition by means of properties of x. Oops. We want to glue on the boundary T to T bar. So it's good enough if the dx field is gluing up to a sign. So having an offset by a multiplicative minus sign is no problem in view of the quadratic formula for T. Okay, so here we are just rediscovering Dirichlet and Neumann. Now in a way, more formal way as before. So this is the Neumann choice. If del Z equals del Z bar, maybe you already anticipate that this will identify alpha equal plus alpha twiddle. And indeed, if you relate the sigma derivative, which is said to vanish in the Neumann case, to the Z and Z bar derivatives, I mean the usual conversion between tau sigma into light cone, then you find this. And here is the second solution. You just glue the derivatives on the boundary up to a minus sign. And here you set to 0 the tau derivative, which is a vanishing tau derivative is a consequence of fixing the endpoints to Ci and Di once and for all tau. Okay, so if you didn't know about that trick to derive Dirichlet and Neumann from variation of action, you can just walk the formal path right here, and this is working perfectly standalone way. So there is a very formal approach to boundary conditions in more general CFTs, where you ponder about how you solve the gluing condition. I mean, there are Western-Mitten models where you can construct the energy momentum tensor from certain algebra elements, and then it can happen that you not only have a discrete minus sign for the construction of boundary conditions, but perhaps a full SU2 full of admissible boundary conditions. But okay, let's restrict our attention to the free boson. As I was alluding to, you can again patch together the information of del x on the upper half plane together with the information of the anti-holomorphic derivative, again just on a half plane. So you can again use the fact that two half planes combine to a full plane. Yeah, similar trick as played for the energy momentum tensor. So that single field will again receive superscript OP. And this is the one that appears in the CFT description of open string states, again via vertex operators. And yeah, it is doing exactly what we expect by the discussion of oscillators on the above board. There is only one species of oscillators. So maybe we want to give them an OP superscript to be even clearer than we were on the board above. Good. These are all the CFT prerequisites that are needed for a tidy description of the vertex operators. So now we repeat more or less what we did at the beginning of this morning, that we look at how we can construct a suitable field correspondent for physical states, how we can do this in a diff cross-Weil invariant way, and what this implies for the admissible M squares and the admissible polarizations. So now we are ready to construct in a covariant way the open string spectrum from open string analogs of vertex operators. Again, they are going to be the field correspondence of physical states. But one difference is, well, in the closed string case, I argue that we should integrate them over the complex plane to avoid a singling out of a particular point z. And here in the case of the boundary, here it's enough to integrate over the boundary. I mean, we do need to integrate because, again, singling out z equal 2 is very much at odds with diff cross Weil. But now there is only a reduced diff cross Weil. So integrating over the boundary is enough to invariantize. So integrated over the boundary. And of course, this perfectly lines up with the intuition that inserting an open string state to the worldsheet, well, open string worldsheets always have boundaries. So adding open string states should better couple directly to the boundary. Okay, so this is the way how open string vertex operators can be combined to diff cross Weil invariance, or this is a necessary condition. We still need to make sure that V open transforms in the right way, that it eats up the transformation of dz. So you would probably be tempted to say, of course it has to be a conformal primary field of weight 1, but let's be sure that we are on the same page what we mean by conformal primary field. With respect to which energy momentum tensor is that the case? And perhaps all the abundance of superscript is suggestive, of course it should be a energy momentum tensor with the same superscript structure. We need a conformal primary with respect to the T-open energy momentum tensor constructed in the above case. Okay, so you have to check out the OPE of such a candidate vertex operator with the open string incarnation of the energy momentum tensor. Okay, you can probably imagine how these calculations look like in practice after what you have seen in the closed string case. And there is yet another element from the closed string construction which goes through in reasonably literal form. We want to have momentum eigenstates, but you saw above that momentum is only okay in the Neumann directions. So I still want an eigenstate with respect to alpha 0, but now I look at a truncated version of this alpha 0 mode in those directions where it is allowed. So this is only in the Neumann directions, not in the Dirichlet directions. Okay, and in order to get such eigenstates for momentum, I once more need a plane wave. And now this plane wave is only involving a momentum vector of reduced size. So now I'm writing down a plane wave where, formally I give this P a Neumann index A. And I contract it only in the Neumann components of this X open. Yeah, so momenta are in not in R1, D, but in R1, P. And as in the closed string case, there is now some decoration here denoted by phi open that describes everything else which is not the plane wave. And a more precise characterization of not being a plane wave is that it is only allowed to have differentiated axis. And okay, just to be very clear, the kind of derivatives that we can do for insertions on the boundary are those along the boundary. So this is, here I'm writing T as one way of addressing the coordinate on the boundary. So it's, if you wish, in the Neumann case, the dz and the dz bar at the same time. So these derivatives along the boundary, these are the field correspondence to saying I'm introducing an oscillator. Now this open string incarnation of the oscillators. And in fact, now these differentiated axes, the decoration, this can be in both the Dirichlet or in the Neumann boundary conditions. So here I was really meaning it to write mu. It's either one Dirichlet index or a Neumann index. So in contrast to the plane waves, the decoration can be in either direction. Yeah, these are the ingredients and rules for open string vertex operators. And let's translate the conformal weight contributions into the admissible masses. So now there is a little difference to the factor of 2 management. It would take me very long to explain it in all details, so I might go over it rather quickly if you don't mind. So this time, the plane wave, it no longer contributes a quarter alpha prime p square, but here it's with an extra factor of 4 in comparison to the closed string. This has to do with how one constructs the Green's function. I will in fact give a semi-precise explanation in tomorrow's lecture when we compare open and closed string Green's functions. Okay, and yeah, once more, these admissible ingredients of the decoration phi open can only have an integer contribution to the conformal weight. So let's put this integer nature of h phi together with the mass shell condition that whatever we find for minus p square is equal to m square. And from this we find almost the same story as for the closed string, only with an offset by a factor of 4. No, sorry, this is not called offset. It's just a rescaling of the entire spectrum by a factor of 4. So the admissible m squares in the open string case, these are all the integer multiples of 1 over alpha prime, where the integer is no more negative than minus 1. So this is to say that as in the closed string case, there's a single tachyon, namely from the simplest choice of decoration being the identity operator. So this is really super analogous to the closed string. If we send the decoration to be 1, then you can immediately get a tachyon from a plane wave with nothing else. So this is the simplest example. Once more, the momentum is now constrained to be in Neumann direction. And please mind the factor of 4 in comparison to the p square of the closed string tachyon. And perhaps it was already reasonably clear, but I can't resist saying it once more. The only admissible ingredient for the decoration is a boundary derivative, and it does not distinguish between z and z bar. So all this combinatorial complexity of the closed string from keeping the del z's apart from the del z bars, we don't have to worry about this here. Loosely speaking, the open string spectrum is the square root of the closed string spectrum, and I guess this will become pretty obvious when I go through the massless states in a minute. Maybe not in a minute, but in 5 to 10 minutes. Yeah, so simpler polarizations. Or putting it differently, the closed string polarizations are something like a double copy of the admissible open string polarizations. Because the way how you solve the primary condition for T open, this works in exactly the same way as you solve the primary conditions in a chiral half of the open string. If you ignore all the z bars in the closed string and solve the primary condition for T, then the computational mechanics is identical to the way that you parse the T open. Yeah, loosely speaking, the closed string spectrum is a double copy of open string spectrum. I very much hope to get to the point that I discussed string amplitudes in the depth, that I can show how double copy goes through, even for the tree-level amplitudes. That not only the spectra are related by double copy between open and closed strings, but in fact the tree-level interactions. And it's a vibrant research program to check out to which extent this goes even to the loop-level interactions. But yeah, that's something for later. For now, it's definitely time that I introduce the notion of D-brain. So these were the formal prerequisites to understand what's going on with the open strings. So this was a more formal discussions of the rules of the game, and now it's time to fill all of that with more physics. So the highlights of this next section are both D-brains and non-abelian gauge theory. In case you got a bit dizzy from all the statement of rules, this is now an excellent moment to wake up. Yeah, so you probably... Also the iPad listened to my advice to wake up. What was I saying? Maybe you found it very much ad hoc that I separated the space-time directions into Neumann ones and Dirichlet ones. So there was a very undemocratic distinction of the Lorentz indices mu into the Neumann choices, denoted by A equal 0, 1, ... p, and then another species of index I, which was running over the Dirichlet directions. So clearly, what we have done in that process, we have decided that the open string endpoints are trapped in non-trivial subsets of Minkowski spacetime. I mean, if you draw all the Neumann directions as if they are spanning a hyperplane, sorry about this very cheap projection here. So the Neumann directions are in this hyperplane, and yeah, this is where the open string endpoints are allowed to hang out. Or putting it differently, by imposing Dirichlet conditions, you forbid endpoints to move in the Dirichlet directions. Because in the Dirichlet directions, you single out a specific value of these Ci's and Di's. So endpoints are trapped within the Dirichlet directions. They are bound to live in these hypersurfaces of spacetime. And yeah, given that there are p+1 admissible Neumann values of the A index, we are here talking about hypersurfaces of dimensionality p+1. So this is where the open string endpoints are still allowed to move once we have specified our choices of Dirichlet and Neumann boundary conditions. So they are this plane I drew, this hyperplane, is formally defined by, remember, at the endpoints I want to be at Ci in case of the first endpoint and Di in case of the second endpoint. And these hypersurfaces are known under the name dp branes. So this p number that I keep on using to count the number of spatial Neumann directions, this is also entering the name of these d-branes. So if you are lazy and don't want to state the dimensionality, you say d-brane. But if you want to be precise and state the dimensionality, you speak of a dp brane, which may specialize to a d3 brane, d25, and so on. Okay, so this is the terminology. One can argue whether it's good or bad that there is an offset p+1 for the dimensionality, but this is how the conventions are, and I will swim along. Yeah, what can one say about these dp branes? So first of all, from the viewpoint of symmetry aesthetics, one may find it slightly offending that the Lorentz symmetry is broken, or at least the Lorentz symmetry one would have naively expected from the Minkowski spacetime where all of this is happening. So in the moment that you separate the Lorentz indices into Neumann type 1s and Dirichlet type 1s, in that moment you are losing the full Lorentz invariance, and what you preserve is a subgroup. Well, you still have Lorentz symmetry within the Neumann directions and separately rotation symmetry within the Dirichlet directions. So once more, the assumption is that x0 is receiving Neumann conditions. That's why I am quite clear about the signature, that here is the Neumann block, including the time direction. Yeah, it doesn't sound that good if symmetry is lost, but the mindset about all this is, it's not the property of the fundamental theory. It's more the property of these D-branes. And the idea is that the D-branes are viewed as dynamical objects that are moving around in a theory which starts out being completely Lorentz symmetric in all the space-time dimensions. So morally, Lorentz symmetry is there. It's just that the dynamics of the D-brane, we see it a bit frozen here. So the idea is that the D-branes, in the way we encounter them right now, come from an initially dynamical object, which moves around in a fully SO1, D-1 symmetric theory. And yeah, how come that we are not seeing this in the description we are making here? So sadly, we only have partial control over string theories. What we do throughout these lectures in most of the textbooks is a perturbative description of string theory. And in this perturbative description, we have a hard time seeing all the beautiful properties of D-branes. So if we were to break out from this perturbative description, the D-branes have a mass, or a tension to be precise, that goes inversely with the string coupling. And in everything we do here, I keep on saying perturbative, and this in turn means that the string coupling is supposed to be reasonably small. But if D-branes have a mass that goes like 1 over string coupling, then it becomes infinitely heavy. So in that sense, you are freezing all the dynamics of the D-brane. In the discussion here, the D-brane appears more static than it is in truth. This is not an artifact of the theory, but this is the artifact of our description, or an artifact of the fact that at the moment we have more computational control on the perturbative side. Yeah, so let me try to summarize this briefly, what I was saying in words, that there is a tension to all of these DP branes, which depends on the string coupling, and in particular, that tension diverges in our perturbative angle taken throughout the lecture. Or dynamical D-branes are non-perturbative phenomena. This is maybe how I should phrase the statement in a more positive way. Of strings. So therefore, because of their divergent tension, they appear infinitely rigid. Okay. Yeah, I'm sorry for this disclaimer. I won't make it beyond that perturbative perspective within this course. Is it fair that the Johnson textbook takes people partially outside perturbative? Yeah. Okay, maybe one choice to read beyond that is Clifford Johnson's textbook on D-branes. Okay, this is the end of that more bird's eye comment. Now I want to get back to some hands-on constructions and apply those rules, which are still scattered on some of the above boards. So now I want to deliver the non-abelian gauge theory part of the headline. So the non-abelian gauge theory will be found in the massless sector of the open string excitations. And well, we have already covered the trivial choice of the vertex operator decoration when h phi is 0. So the next case to study is h phi equal to 1, where the decoration is, well, a single derivative of x. But that can be both in the Dirichlet direction or in the Neumann direction. It can be on the brane or perpendicular to the brane. Yeah, and as you can imagine, it's getting tedious to keep all these superscripts OP running. So I'm suppressing both the specification of worldsheet boundary derivative, and more importantly, I'm suppressing the superscripts to avoid cluttering in all of for all the objects which sometimes carried this superscript. Yeah, there are these two choices, whether the polarization is in Dirichlet or in Neumann direction. Let's start with the Neumann one. This is, let's call it zeta A. I need a polarization vector to soak up the single vector index of dx. And so this is a polarization on the brane. And the vertex operator Ansatz, yeah, let me be clear that this is for the moment an Ansatz. This, well, is a vertex operator parametrized by admissible polarization vectors, and it has this combination of plane waves and partial A, and yeah, massless as promised. And once more, you have to check that it's really a primary field with respect to the open string analog of the energy momentum tensor. So following our agreement to suppress the superscript OP, the statement is that the OPE with T has to give, well, what you get for primary fields, namely double pole and simple pole. This is what we want, but unfortunately, what we get is a triple pole with a residue proportional to, essentially zeta dot p, together with yet another plane wave. Okay, so it's exactly the same situation as we had it in the closed string case, that there is a obstruction to being a conformal primary field, an obstruction which we can get rid of by tuning the polarizations appropriately. So here we once more need a transversality property that the polarization contracts to 0 with the momentum. Okay, maybe I should be writing a dot product. I'm a little bit hesitant to do it because dot product was used before to contract over all values of mu. And here, of course, this is a vector of S1, SO1, P, namely over the Neumann directions only, on the brane only. Yeah, the physical state condition is take polarization vector zeta and kill a single component, namely kill the component, well, which is in momentum direction, so to say. And therefore, there are numerous solutions, numerous physical states, but some of them once more decouple. There's once more spurious states that we need to subtract. There are fewer opportunities to create spurious states because we only have one species of derivative, this boundary derivative that I don't even decorate anymore. And specifically for mass level 1, the spurious states are derivatives of a naked plane wave, which are taking this form and can be lined up with polarization vectors zeta if you send zeta to the momentum dead on. And I mean, they are physical as well, the spurious polarizations. Just check whether this or not is kind enough to contract to 0. And since the momentum squares to 0, yes, these are manifestly physical ones as well. They are physical, but boring, because they decouple. They are total derivatives which integrate to 0 over the way we are supposed to integrate open string vertex operators, and one still needs a couple of refined considerations to show that this is really the case. Okay, so when you ask about the non-trivial physical states, which have non-zero norm, then it assembles to spin 1 polarization with the transversality condition and with a gauge freedom. I mean, this spurious state simply means you can add that one without changing anything, any interactions or amplitudes of that state. So, like in the case of the closed string polarization, there is a gauge freedom by this shift here. Add your favorite multiple of the momentum vector to zeta. Okay, and once more, with these conditions, you can tell uniquely what that physically is, that polarization. It is a gauge field. I mean, the catalog of properties being spin 1 and having that gauge freedom and transversality, this is enough to say it must be a gauge boson. Okay, it's not telling you whether there are higher derivative interactions or not, but yeah, these are exactly the defining properties of a gauge theory. So this Neumann polarized vertex operator describes gauge fields on the DP brane. Where the number of physical degrees of freedom is p minus 1, so it's by 2 units smaller than the dimensionality of the D brane. I mean, this is analogous to how electrodynamics works in 4 space-time dimensions. I mean, the photon has a plus and a minus polarization, or plus and minus helicity. So it has 2 polarization states, which happens to be 4 minus 2, number of space-time dimensions minus 2. And similarly here, you are doing this now counting the space-time dimensions on the D brane. So we do get a gauge theory, but a gauge theory which only lives on the brane. But closed strings, in turn, don't care whether there's a D brane or not. I mean, the closed string doesn't have an endpoint that you could potentially confine to that brane. So it's quite funny. Gravity works in a higher dimensional way, but the gauge theory is confined to a lower dimensional object. And this is at the root of an explanation why gravity is weak. I mean, you all know gravity is such a weak force, the entire attractions of the Earth is compensated by the electromagnetic repulsion of this floor. Electromagnetism is very strong in comparison to gravity, and that D-brane picture explains that well. If the D-brane is lower dimensional than overall space-time, then the field lines have fewer directions to escape into. But gravity, in turn, gravity is also working in the transversal direction, in the Dirichlet ones. So the gravitational field lines are getting massively diluted with all these extra dimensions they have for their disposal. So this is a possibility to explain why gravity is the weakest of the interactions. Okay, all of this was hopping out of the Neumann polarization, and we are not completely done with the massless states, because I have so far neglected the Dirichlet polarizations. So what if I pick the d-axis in Dirichlet directions? So then I need to contract with an object that carries an I-index with the usual range in the Dirichlet directions. And yeah, this associated vertex operator takes the following form. And yeah, note that the plane waves and the decorating dx have no direction in common. I mean, the momentum is only in Neumann directions and accordingly projects the x in the plane wave. So this is the complementary directions as compared to those which are in the decorating dxi. So therefore, you don't have any trouble with physical state condition or gauge freedom, given that these are in different directions. We can immediately close the book and say these are the physical states and the non-trivial, non-spurious ones. So for these Dirichlet polarized states, there is no non-trivial transversality condition or gauge freedom. Yeah, and from the viewpoint of the gauge theory on the plane, I mean, this gauge theory on the brane, I'm sorry. For the gauge theory on the brane, I would describe it in terms of a Lorentz symmetry here. And these scalars that are just constructed, these states that are just constructed are scalars with respect to this Lorentz symmetry on the brane. So for their classification, scalars with respect to this Lorentz group on the brane. And there's a nice interpretation to it. You can interpret these scalars as being the fluctuation of the brane as it wants to move a little bit. I mean, as I was saying, in this perturbative approach, the tension diverges, so it can't really move, but you can still study infinitesimally the attempts of the d-brane to move. So it's the fluctuations of the d-branes that are encoded by these scalars. Or if you manage to give them a vev, then it means that you have actually moved the d-brane. So interpretation of these scalars are the transverse dp brane fluctuations. Yeah, this is concluding the massless state construction, and I guess for the massive ones, for even larger values, h phi equal 2, 3, ... and higher, there's nothing new that I can say what you haven't seen in the closed string case before. Just throw away the z bars and identify all the z's in the closed string discussion with this boundary derivative here. So I guess we won't need any detailed discussion of the massive states. There's only one element of zoology that you need to keep in mind. The polarizations can now have different numbers of Dirichlet and Neumann components. So if there is any kind of bookkeeping challenge, then it is about keeping an eye on all the choices of Dirichlet and Neumann. But it's for sure the square root of the number of the states at each level than what the closed string spectrum has to offer, mass level by mass level. Good. It's 20 past, and there is still one page of things that I want to say. Oh, yes. Okay, yeah, this is a good point. Yes, even though I will do perturbation theory in the next section, yeah, I don't. You're right. It's not really visible. Where did I use perturbative description? Do you have a quick answer, Carlo?
But this is free theory. I mean, he's doing free theory, so it's not even perturbation theory. Now it's just looking at free wave equations. Yeah, so, but you're saying that we cannot see the dynamics of the grain because we are doing some perturbative stuff. So I was wondering. You have to switch on the string coupling that he didn't do this already, and he will explain us what happens when the string coupling will be switched on infinitesimally and things will start to interact. So at the moment there is no interaction. Right? Am I saying?
Okay, I was about to say at the beginning of the amplitudes discussion that the free theory looks the same as the interacting theory. That's why I was hesitant to answer.
Is there an answer maybe for the grains that we are neglecting, maybe just considering free bosons?
I mean, there is indeed a brain action, but this is like a low energy effective description of what we find for the string interactions. So with the formalism you will see for scattering amplitudes, you will produce gauge boson amplitudes and they're alike. And if you reverse engineer which action generates those from its Feynman rules, then you arrive at D-brain actions. And they're actually pretty analogous to the worldsheet actions. It's essentially world volume of the D-brain. You see induced metrics, pullbacks of the space-time metric onto the D-brain, and yeah, things like that you can extract from the low energy regime of string scattering amplitudes. Yes?
Well, you have those like eyes, so aren't they like encapsulating maybe the freedom of the brain to like, instead of having like no dynamics, you have those eyes.
Oh yeah, maybe yeah. Your question is at the same time containing the answer to the earlier question, what is perturbative here? Maybe what is perturbative here is that we are looking at the states one by one. I mean, each state insertion some sort of comes with one power of the string coupling. And by saying we are perturbative, we are assuming that there is just a small or finite number of excitations. I gave you one example where I went beyond that. I pointed out that the graviton vertex operator looks like a deformation of the action. And if you pass to a coherent state, then yeah, I mean, each state comes with the power of the string coupling, then you go for arbitrarily high orders. So maybe the serious consideration of coherent states is the way out of the perturbative. Yeah, discussing the states one by one and assuming presence of a finite number of them, that's the perturbative thing of what we do here. Did I get distracted from answering your actual question?
No, that's right.
Okay, I see. Good.
I have another question. How can we provide the debriefs of other fields? You're saying that the excitational the debriefs are gauge fields. Can we have some fields transforming with respect to these gauge fields?
Oh, okay. First of all, important thing, this discussion of the D-brain applies to the entire spectrum. I mean, it's just for timing reasons that I focused all of the discussion on the massless case, but also all the massive excitations will have fields that live on the D-brain. Say if I have two insertions of del X, there will be some polarization tensor, that's a massive spin 2 field living on the brain. And there will also be fields of lower spin when I have a mix of Dirichlet dx's and Neumann dx's.
This way I cannot have massless imaginary fields because all the massless degrees of freedom are packed into the gauge field.
Oh yeah, that's right, that's right.
For example, massless are transforming with respect to these gauge fields on the brain.
Yeah, I mean, the massless fields are, as you say, the gauge fields. And then you said pions. I'm not fully sure whether I would want to call these scalars here pions. I will try to say in the next 20 minutes that they are a bit more like the scalar fields that you have in certain gauge theories, such as n equal 4 super Young-Mills. Oh yeah, did Eli Pomoni get there, telling you about n equal 4 super Young-Mills? Fantastic. You will meet again n equal 4 super Young-Mills, and there, well, the scalars here are more or less like the scalars in n equal 4. I'm hesitant to call them pions, but I understand that people from different communities have different expectations when they hear the word pion. Okay. Yeah, perhaps I should try to get to this point of recovering n equal 4 super Young-Mills, or at least the scalar part of it. Or has a further question on this? Yeah, so far you just saw that there is a gauge field, but I haven't committed yet whether it's an abelian or a non-abelian one. And this is controlled by how many d-branes we are playing with. And I hope that this doesn't sound like a tautological discussion. The idea is that we want to look at a multiplet of coincident d-branes. Of course, I cannot draw coincident d-branes, so I draw them as if they were infinitesimally displaced. But just imagine I take several d-branes and put them literally on top of one another. I insist on top of one another because you saw in the classical m-square formula that each d-brane separation translates into masses. But I want to have a good and rich massless sector, so let's assume they are really coincident. So here the picture tries to convey a scenario of n coincident dp branes. Choose your favorite value of p, choose your favorite number n, and for n such coincident d-branes, then there are a lot of choices for each open string excitation. I mean, there are two endpoints that you can formally associate to any of these branes. So let's say one of the endpoints I associated to the third brane, and the other endpoint associated to the first brane. So you have a total of n squared choices how you make these assignments. So there's one choice per endpoint. Let's use m and n for these endpoint labels. So taking both endpoints together, there is a total of n square choices to be associated with one of the coincident branes. So this little m is counting the branes, so it's the brane number, so to say. And there's really an independent choice, as visualized here, where the two endpoints are associated with different branes. And formally speaking, it implies that the entire open string spectrum becomes matrix valued. And at no cost of m square. I mean, m square would arise if I were to separate the d-branes, but at the moment we are not doing that. And this really concerns all the states, both the tachyon and the gauge field and the scalar companion of the gauge field and anything massive. So all of these states, the entire tower becomes is promoted to n by n matrices. So instead of talking about a single physical state, say at the tachyon level or for a given polarization direction, I should instead talk about a matrix worth of such physical states labeled by these integers m and n who track the d-brane association. Okay, and in order to be a little bit closer to the conventional description of gauge theories, the non-abelian ones, it's convenient to change bases. I mean, being matrix valued probably sounds like going in the right direction. And one way how I can span real n by n matrices is through the generators of the Lie algebra of UN. So the change of basis I'm advertising is the following. The m and n specify an entry of such matrices. And I look at n square choices of these matrices labeled by an index A, and that index is to be read as an adjoint index of UN. So in the step from here to there, I did the change of basis. Oops. To n square generators. TA of UN, namely Hermitian n by n matrices. And these matrices also have the nickname Chan pattern factors. So if you want to read up on them in textbooks, you will frequently find them under this name. So as I was saying, this index A is to be read as a UN adjoint index. A equal like that. Yeah, so for two d-branes, you have a U2, which contains the Lie algebra of SU2. Say the three Pauli matrices are a possible basis. And there's a fourth generator responsible for the U1 part, which you can take to be the unit matrix. Okay, so this is the way how non-abelian gauge interactions arise. So specifically, the gauge bosons in the massless sector, they form an SUN Young-Mills non-abelian gauge theory on the brane. And okay, this is not the full story, only the low energy limit of that string theory is a Young-Mills gauge theory. I mean, this would be the final word if the gauge bosons were alone in the world. But there is always this infinite tower of additional excitations, and they have plenty of fields on the brane at each mass level. And all the rich interactions of the gauge boson with the rest of the open string spectrum, well, this gives a tremendous enhancement far beyond gauge theory. You can describe it in the low energy expansion, and then you see higher derivative interactions. But also, it's worthwhile to keep the energy arbitrary, and then we will see at the level of gauge boson amplitudes that there will be all kinds of poles which reflect the exchange of the additional states in the spectrum. But yeah, already here we see Young-Mills gauge theory on the brane emerging. And so far, I have kept the multiple d-branes coincident. Now, the last thing I want to do for today is to pull the branes apart and to reproduce yet another piece of standard model physics, namely the Higgs effect, or a small variant of the Higgs effect where the scalars are adjoint and not fundamental. Yeah, last thing to look at before lunch. Now let's separate d-branes. And the very first thing to be said is that symmetry gets broken. I mean, this UN gauge symmetry can no longer persist as we move the branes apart, simply because there will be masses getting kicked on. Whenever you have an open string whose endpoints live on separated branes, they're immediately m squares. And that's the simplest way of breaking gauge symmetry, giving some of the fellows masses. So the breaking goes into u1 to the n if you move all the branes apart from each other. And now, to illustrate what I meant before by Higgs effect, let's look at the n equal 2 case in all detail. Let's suppose we initially had two coinciding d branes, and then we took the decision to move them apart. Okay, so let's say one of the d branes is at position ci, the other brane is at position di. So here is the ith direction plotted. And with n equal 2, it's easy to draw the four possibilities how the endpoints of open strings can be arranged. There are the quote-unquote diagonal ones, where both endpoints are on the same brane. And then there are the off-diagonal open strings, where the endpoints are on different d branes. So strictly speaking, I should be drawing two of them, because you clearly can form two off-diagonals in a 2 by 2 matrix. And here the concrete Chan-Paton factors associated with the diagonal and off-diagonal cases. They go as follows. Here are the Chan-Paton factors for the off-diagonal states. Among the four choices of 2 by 2 matrices, here are the two off-diagonal ones, or a choice of the off-diagonal ones. And the entire spectrum of the excitations on that red string acquire the following mass shift that I already alluded to a couple of times, namely the extra contribution to m square, which depends on these c's and d's. They go like 2 pi alpha prime square. So I think you saw the formula before. This is the same formula was there in the classical case, and also in the quantum, after quantization, the offset to the m squares is still the same. Good, this is the mass shift applicable to the entire tower, and the tower in turn comes from the same mass formula as we had it before. So this is literally the same mass square formula that we had in case of a single d brane, and that goes through to the diagonal states with both endpoints on the same d brane. This I dare to call a geometric Higgs effect for the following reason. Or more precisely, the process of pulling the d branes apart, if they were initially coincident, this pulling apart triggers a Higgs effect. Among these off-diagonal states, let's look at the gauge bosons, or those vectors which are initially massless. Giving those a mass is exactly the same story as the fate of the W bosons in the standard model. So this leads to a pair, W plus minus bosons. And maybe you noticed the discrepancy between the buzzword Hermitian and these choices here. I took the liberty of combining the Hermitian-Pauli matrices in a certain way, like sigma 1 plus minus I times sigma 2. So in this way, I'm going into the complex spaces that you saw in the standard model to isolate the W plus and the W minus boson. If you don't like these complex combinations, feel free to rotate them in your preferred way. Okay, so pulling apart gives masses to 2 out of 4 gauge bosons. I mean, the diagonal ones still stay massless. This is the story for the Neumann polarizations. And then there were these scalars in the initially massless sector. So for the scalars, you give the diagonal scalars a VEV. I mean, I told you that these scalars describe a d-brane fluctuation. And fluctuating around what? Fluctuating on the one side around their VEV, but on the other side, fluctuations in a spatial sense, that's a fluctuation around C and D. So this is a complicated way of saying that the Ci and Di are simply the VEVs of the respective scalars. And it's only the diagonal ones that get a VEV. I mean, also the scalars can come with 4 different Chan-Paton factors here, and the VEV is given to those which are diagonal. So where both the row and the column indices agree that they refer to, say, the first brane or the second brane. Yeah, so these indices refer to here. These open strings are the diagonal 1-1s. Those indices are the diagonal 1-2s. And that string in the middle is covering both this and that. Yeah, these acquire a vacuum expectation value from dp brane position. Okay, and yeah, it's 2 commonalities with the Higgs effect of the standard model. Gauge fields becoming massive and scalars acquiring a VEV. And the only mild difference is that the scalars here in the open string case have the same adjoint index like all the other states. So it's a quite brutal way here of introducing gauge degrees of freedom, like everybody is automatically adjoint. And okay, here I'm still looking at strings that are confined to 1 stack of d-branes. There is a way to go beyond adjoint matter, but this is a slightly more sophisticated trick. I won't give a detailed discussion, but maybe I should mention it by all means for your entertainment. So if you're tired of adjoint gauge degrees of freedom and want to see fundamental gauge indices or bifundamental ones, then you can go for intersecting d-branes. So replacing this one. Whoops. This is coming from intersecting d-branes. So imagine there is 1 stack of d-branes like that, and yet another stack going like that. Then so far I was telling you about strings that do this, or possibly do that. But another and very exciting scenario is that we stretch an open string state in between different such d-branes. And yeah, this is how you can implement chiral matter in string theory. If you have more than 1 stack of d-branes, and then depending on the intersection angle, this gives rise to chiral matter, which may or may not have a mass shift from intersecting d-branes. So here, for the 2 stacks that I was drawing, I mean, here's a triplet of branes that give rise to a U2. Here is a doublet that gives rise to here's a U3, here's a U2. And if you ignore the U1 that is hidden in both, this is pretty close to the strong and weak sector of the standard model. So ignoring the respective U1s, you could, for instance, interpret those strings here as giving rise to the gluon through their massless excitation. then here the U2 is looking like the weak sector before electroweak symmetry breaking. So this is the massless precursor of W and Z. And here, those open strings, this is something which participates in both of these interactions. Fundamental with respect to the U3 strong and fundamental with respect to the U2 weak. So question to you, do you have a standard model particle in mind that fits this description? Oh yeah, would you have a standard model particle in mind that fits the description of that open string here, having a fundamental SU3 and having also a fundamental SU2 index? Yeah, exactly. This is a quark. More precisely, this is a left-handed quark, because only the left-handed ones participate in the weak interaction. Okay, so you can see that this is a possible avenue you can take into string phenomenology, getting closer and closer to the standard model gauge group. But of course, there is more and more burden if you want to make this fully accurate. I mean, we are still lacking some U1 hypercharge. Spoiler, the U1 hypercharge is unfortunately not the respective U1s from here. And furthermore, there are various consistency conditions from string theory on what an admissible D-brane configuration is. And among other things, consistency requires you to have two other D-branes, like another U1 brane and a fourth U1 brane. So you need a quite sophisticated quiver to obey these consistency conditions, such as tadpole cancellation. So I think one famous quiver that contains standard model gauge group is sometimes called the Madrid quiver. Maybe the textbook of Ibanez Uranga could be a place to consult about this. But okay, all this to say, chiral matter comes from intersecting D-branes, and then engineering standard model-like gauge groups is a matter of studying admissible D-brane configurations. And you can go all the way to properties of the standard model like number of generations. How to see from the D-branes that there are 3 generations of quarks, leptons, and their alike. Number of generations comes from intersection numbers, how frequently these stacks of D-branes intersect one another. Okay, this is probably hard to think about. I haven't told you about the geometry where they are living. What you don't see from that picture is that these D-branes are conventionally wrapped about certain cycles of Calabi-Yau manifolds and alike. So you need to know something about Calabi-Yau geometry to appreciate these intersection numbers. And these intersection numbers are controlling the number of generations. You are about to ask something? Oh, absolutely. I'm doing a pretty brutal move that I will also do in the next comment on N=4 super Young-Mills. I have secretly assumed that these open string excitations also have fermions in them. Sorry, I should have made a disclaimer on that. So with the material that you saw on the blackboards, this is not about the fermions themselves, but about their scalar partners. So even with some D-branes, you will usually preserve a certain amount of supersymmetry, and then these quarks come in a chiral multiplet together with a scalar partner that you can call squark if you wish. Yeah. At the level of conformal field theory, you need so-called boundary condition changing operators, or twist fields. They have pretty nasty correlation functions. Okay, let's not get late for lunch and make sure that we have seen where N=4 super Young-Mills is coming from. So assuming that all the comments on the D-brane foundations go through to the superstring, if you do 10-dimensional superstrings with the choice of p=3 with D3 branes, then the massless open string excitations give you a four-dimensional gauge boson. And then when D is 10, there are exactly 6 scalars at the massless level, 6 choices of these var phis. And what I didn't tell you about, what we'll try to tell you about tomorrow and Friday, is that there will be space-time fermions along with that. And even before looking at the fermion sector, this composition of gauge boson plus 6 scalars, this is exactly what we find in the n equal 4 super Young-Mills multiplet. This is the maximally supersymmetric gauge theory with n equal 4. So this is the calligraphic n, counting the number of supercharges. Don't mix it up with the gauge group, because the gauge group can be whatever you like in this case. I mean, we are getting one species of this multiplet per Chan-Patton degree of freedom. Or saying it more clearly, this multiplet is living in the adjoint representation of UN. So this is the stringy engineering of four-dimensional super Young-Mills. Or most naturally, you start with a D9 brane space-time filling where you have a 10-dimensional gauge field and there is a dimensional reduction mechanism to get to maximal SUSY. But there are many physically important features of D3 branes which are at the heart of the ADS-CFT correspondence and which I'm sure Alberto will tell you more about tomorrow. Okay, so this is a sneak preview of where n equal 4 super Young-Mills will be. Good, that's it for today.